In this example exercise, we will see the effect of a coarser feed size on the feed belt to a SAG mill. So this plant has already been calibrated. So previously we entered survey data, performed a mass balance, and then calibrated the models. If we have a quick look at the SAG mill here, when we do a simulation, we can change certain conditions around the SAG mill. So for example, we can change the discharge grades at the end of the mill, the operating variables, the water addition, information about the ore properties, as well as the calibration constants. These calibration constants are the result of the previous calibration process. If we have a look at the feed belt going into the SAG mill, which is the subject of this video, we can see here that we have a throughput of 3,000 tons per hour, and during the calibration we used 150 millimeter for the feed. That is the shape of the distribution. So if we have a look at our simulation results with this information, we can see that red icons indicate potential problems and blue icons show good operation. So if we have a look at the SAG mill, we can see our power draw, our total filling, and our slurry filling, and these are all within acceptable parameters. So let's look at the feed on the conveyor belt. Now on your plant, it is possible that this F80 on the belt will change daily. So the crusher plant may call and say, instead of 150 millimeter, which is the usual size, we are giving a much coarser feed to the SAG mill, or perhaps a much finer feed. In this case, we need to be able to make a quick decision on the plant on that day on how we are going to deal with this situation. So in that case, we will perform a simulation using the coarser feed. Now here we can see we are still experiencing some problems in the secondary circuit and in the SAG mill. So let's have a look at the SAG mill. Now here our eye is immediately drawn to two problems. Firstly, the power draw has gone red, the total filling is still okay, and the slurry filling has gone red. So in the advice column, we receive advice about the problems that we are experiencing. So firstly, the predicted mill power was higher than the installed motor power. So the software gives us advice on how we can deal with this problem. So we can consider decreasing the ball load, reducing the mill speed, or reducing the throughput in the next simulation. On your plant, if you experience this type of issue, the throughput would have reduced automatically as a result of your control system controlling the load. Furthermore, slurry pooling could be a problem at these conditions. So slurry pooling basically means that the charge inside the mill splashes into this slurry pool instead of braking against the toe of the charge. So with slurry pooling, you are reducing the impact breakage in the charge. The software tells us that we could consider changing the mill speed to solve this problem. So out of the simulation, we can see that changing the mill speed would probably be the most viable option of what you can do. So if we have a look at our SAG mill conditions, we can see on the operating variables that speed is one of our options that we can change. So I'm going to reduce the speed to 71% and see what happens if I do that. So after I make a change, I can press simulate, and now I can see that my SAG mill has gone blue again, which means that my SAG mill results are within reasonable bounds. So let's have a look. Our power draw is below the maximum. Our filling is higher. The reason for that is that we have reduced the mill speed. And then we have a slurry filling of 100%, which is quite a good number. If you wonder why the power draw has gone down when the mill feed has actually increased, the reason for that is that the mill speed has gone down, and the mill speed affects the power draw.